Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss the molecular term symbols for the diatomic molecules, whether the molecules are your homonuclear diatomic molecules or the heteronuclear diatomic molecules. I'll discuss the method of the determination of molecular term symbols for both kinds of the molecules. Okay, so before going into the details of the methodology, how to actually determine the molecular term symbol, it is very important to know the importance of the molecular term symbol. See guys, it is very important, right? Since you know these diatomic molecules, they have the very large number of the excited states, okay, and all these excited states basically are designated by the molecular term symbols, okay, and these molecular term symbols for excited states is very important, or say you can say the very helpful in the interpretation of the electronic spectra. Okay, so it is generally the molecular term symbols actually are needed for the interpretation or the study of the electronic spectra of the diatomic molecules. Okay, so first of all you should know actually what formula we can use, and then we will see what are the different terms used in these molecular term symbol. Okay, so see, if you are talking about the homonuclear diatomic molecules, so I am writing here homonuclear diatomic molecules. Okay, so they could be your hydrogen molecule, okay, your helium molecule, okay, and if you continue in that manner, okay, then you may also take the example of the lithium, okay, then your beryllium, Be2, okay, then your boron, right, then carbon, nitrogen, oxygen, fluorine, etc. Okay, and you may also take the example of the neon if you want to take. Okay, see, however, it is not possible that see, I'm not saying that this neon is stable, but you for the sake of the practice you may go for this neon also. So these are the homonuclear diatomic molecules, and the formula for the determination of the molecular term symbol actually is this one. This is a kind of sign which is generally known as the lambda, and this lambda as superscript may have the positive and negative sign, okay, and as subscript it may have G or U, like G-rayed and unG-rayed, okay, and then it may have another thing here, that is 2s plus 1. So this is the formula which we use for the determination of the molecular term symbols. Now what are the different terms in it? See guys, if you know what is delta, what is the meaning of this delta is actually, right? So delta basically is a kind of the quantum number, okay, and this quantum number is used for the resultant angular momentum. You know, angular momentum, see, individual electrons will have their angular momenta, and these angular momenta actually will couple to give the resultant angular momenta, and that resultant angular momenta is what basically ml, which is what the absolute value of the your ml. Okay, so this ml is basically is the resultant angular momentum. Okay, so I can write it here, resultant angular momentum, resultant angular momentum. It is very important. So how we can calculate these resultant angular momentum? Say if you want to know the, so this would be the exact value, right? And then you may take in that manner. Say you are having the one electron, so it may have its own angular momenta, okay, and if you have the second electron, then it may also have its own angular momenta, and you can consider total of I electrons in it, so if it is a multi-electron system. Okay, so these m1, m2 and mi, they are the individual angular momenta of the electrons, and basically they couple to give this resultant value. Okay, and to actually see to designate actually this resultant angular momenta, a particular quantum number is given, and that quantum number is basically is your lambda. This is something very important which you should know. Okay, and one more thing, if you have, say, when you are filling the electrons in the orbital, if you have the sigma orbital, okay, and sigma orbital can be found by any combination. It may due to the s and s overlap, it may could be due to the s and p overlap, it may could be due to the p and p overlap when comes through the axial overlap, okay, and when they when they overlap axially, okay. So whenever your electron is present in the sigma orbital, so then your individual angular momenta of the electrons present in the sigma orbital would be 0, okay. That means there is no net resultant angular momenta when your electrons are there in sigma orbital, okay. So in that case, of course, that resultant value would also be 0, okay, and that 0 will give you delta equals to 0. This is the quantum number actually. So you will remember this particular point. Whenever your electron is present on the sigma orbital, then your lambda equals to 0. Always, it is always equal to 0. That quantum number will always be equal to 0, okay. But if your electron is present in the pi orbital, right, if your electron is present on the pi orbital, okay, so for pi orbital actually you may think in that manner that value of the mi, right, could be plus or minus 1. So what is the meaning of that? Say for example, you are having this pi and this pi orbital, okay. So for this one, it is having the value of the plus 1 and it is having the value of the minus 1, since they are the doubly degenerate, okay. Please remember this particular point. See, this is very important. Now if you see, before going into the detail, you should know the characteristics of this lambda. So I am going to tell you the characteristics of the lambda. So I am writing it here, characteristics of lambda. See guys, this is actually the theoretical background which is must actually in order to understand the concept completely, okay. That's why I am telling you these things, okay. Characteristics of this quantum number lambda. So first of all, you should know this point. This lambda actually is related with the symmetry of the electron cloud with electron cloud distribution with respect to the internuclear axis. Say for example, you are having one hydrogen atom here, okay, and you are having another hydrogen atom here. So there would be the internuclear axis in that case, okay, and you can consider in that manner somewhere here the internuclear axis is there, okay, and that actually this lambda is related with the symmetry of the electron cloud. See, there must be this electron cloud here, okay, with electron cloud, okay. So this lambda is related with the symmetry of this electron cloud distribution with respect to this internuclear axis. This is the first characteristic of this lambda which you must know, okay. And the second thing is that whenever say this was your first point, and your next point, if your lambda equals to 0, I already told you when this lambda equals to 0, there is no net angular momentum. This I already told you, and consequently there would be no degeneracy. That means non-degenerate system would be there, non-degenerate. And you already know this sigma orbitals are actually non-degenerate. So you will remember this point. Whenever you have the lambda equals to 0, so there would be no net orbital angular momentum, and consequently there would be no degeneracy, right? While all other electronic state, okay, so this is one electronic state, while rest of the electronic state will be doubly degenerate. It is very important. So how actually I can explain this point? Say this is the quantum number which I am writing here, okay, and here I am writing the Greek letter to show the ground state, to show the spectroscopic term, okay, and here I can write the degeneracy. And if your lambda equals to 0, in that case you will use that Greek letter sigma, okay, and this would be non-degenerate, okay. And when your sigma equals to 1, then it would be your pi, and this pi is actually doubly degenerate. So I can write it as doubly degenerate. And when your lambda equals to 2, then you may write it as delta, and this delta is also doubly degenerate. And if your lambda equals to 3, then you will use phi, okay, and it is also doubly degenerate. That's why I already told you, whenever this value is 0, it is non-degenerate, okay, and for this non-degenerate state you will use this Greek letter for the for this Greek letter for spectroscopic term, that would be your sigma. It is very important, guys, to understand this thing. So guys, it again, see, it is very easy to actually remember, to learn this thing. So you can use that analogy. You can write it as S P D F, okay, where S stands for the sigma or the summation, P stands for the pi, D stands for the delta, and F stands for the phi, okay. So again, if you want to know, if you want to remember this point, actually how we can remember this, so you simply remember SPDF 0 1 2 3, okay, like 0 1 2 3 SPDF, that means sigma, pi, delta, phi. This is the trick actually which you should remember actually, right? This is something very, very important, okay, very important one. So these are the characteristics actually, and this I already told you. Whenever see, for any kind of the sigma bond, I already told you, for any kind of the sigma bond, regardless their mode of formation, okay, that sigma will always used. See, whenever you have this is another very important point. Whenever you have the sigma bond means your electrons are present in the sigma bond, whether it is 1s sigma, whether it is 2s sigma, or it is 2p z sigma, any kind of the sigma bond is there. So whenever you have the sigma bond, you will always use this Greek letter sigma for the for that quantum number actually, right, to know the term symbol. This is important, okay, for any kind of the sigma bond, regardless the mode of their formation. Whenever lambda equals to 0, you will always use that sigma, okay, and that 0 actually indicates the cylindrically symmetrical electron cloud about the internuclear axis. So these are the things which you should know, okay. So if I go back actually, right, I hope this is now this much of thing is quite enough to understand this lambda actually, right. Now I am going to discuss this S. What is this S? So what I can do now, I am giving you the value of the S, okay. So S is what? Again, it is the resultant spin angular momentum. This S is resultant spin angular momentum, okay. So it's better actually to write it here. So this S actually, this individual S is resultant spin momentum or angular momentum, okay. So this is how. So if you want to calculate this S actually, say for example, so what you will do for the calculation of this S orbital, see, if you have these spins, say this is the one spin, this is another spin, this is another spin, say you are having these three spins. So these would also couple like your orbital angular momentum, like your Mi or M1, M2, M3. So these spins actually will also couple, and they will also give you this resultant value, okay. But the important thing is that you should know actually, whenever you are determining your lambda or your S, you will always focus on the unpaired electrons, okay. So these lambda and S will always be determined for the unpaired electrons. This is important, right? And you know, this 2s plus 1 actually, it is the spin multiplicity. Okay, so these things I have explained you. Now I am coming back to this plus and the minus sign. This is something very, very important. Everyone actually in the lecture, generally they tell, people tell in the lecture that we put plus and negative sign. When you have the sigma, you will put that plus and minus sign, right? And when you have other orbitals like your pi, delta, phi, you cannot put this positive and the negative sign. But actually they don't tell in the lecture that what actually this plus and minus signs are actually, right? So I am going to discuss this plus and minus signs, very important. Okay, so I am writing this here, plus or minus sign, right? These actually signs are only for your sigma, okay, but not for your pi, delta and phi. This you should remember. Now what actually the plus and minus sign? Okay, see guys, whenever you have the plus sign, actually this plus sign and minus sign, they are related with the your vertical plane of symmetry. They are related with the vertical plane of symmetry. So if I am discussing the plus sign, so what is the meaning of that? See, this plus sign indicates that the wave function, right? See, whenever you have the electrons in the orbitals, then in the light of the quantum chemistry, you may have your wave function. Okay, so what is the meaning of that? If you have the plus sign, it indicates that the wave function is actually unchanged or the invariant under the operation of the sigma v, right? And under the operation of the sigma v, and for whenever you have the sigma g, actually for this you will always put the positive sign. Okay, so this is related with the sigma v. Okay, so what actually I am telling you, say for example, say a certain wave function is there, and say for example, see, this is analogy, not the exact one. Okay, and if you put the plane here, say this is sigma v, and if the sign of the wave function is unchanged or the invariant by the operation of this sigma v, then you will put plus sign over there. Okay, and say whenever you are, if you are determining your actually term symbol and you are getting this sigma somehow and with the g rate, then you will always put the positive sign. So please remember this point. If you have this sigma, right, this sigma is there for your resultant angular momentum. Okay, resultant angular momentum. So when you have this sigma, then you can put plus or minus sign over there. But again, you can see whenever your sigma is there with g rate kind of the thing, right, then you will always put the positive, right? If it is not g rate, then you have to decide actually which we will put plus or minus, and there is a method to actually know this thing, and I'll tell you this thing also when I'll go through the problems. Okay, now your next thing is the minus sign. So again, minus sign, what is the meaning of that? Again, if you put that, say again the same thing, this is the wave function and you are putting your vertical plane, and the wave function actually changes its sign actually, right? When it changes its sign or changes its phase, then you will put negative sign. So negative sign indicates that the wave function changes sign or the phase on reflection on this plane, right? That means the sigma v. Okay, and a trick is that, see, whenever you are having spin multiplicity, if you have the spin multiplicity value 2s plus 1 equals to 1, okay, then you will put plus on that sigma, and if this value is 2 plus 1 equals to 3, then you will put minus. Okay, so this you have to remember actually, right? And that sigma may come from your pi orbitals, right? And later I will explain how actually we do that actually in the actual practice. Okay, so I have explained all the things, guys. See, if in this particular formula, if you see here, I have explained your S and spin multiplicity. I have explained why to put the positive and the negative sign over there as superscript. I have also explained this actually lambda, which is the resultant angular momentum quantum number. Okay, now I left with the G and U. So please remember this point. Another very important point, say you are having homonuclear diatomic molecule. I am writing it as here homonuclear diatomics. So for homonuclear diatomics, say you are having, say, oxygen here, okay, or not oxygen, I can make it rather simpler. Say you are having this hydrogen and you are having this hydrogen, basically here, this is the hydrogen molecule, and that point is the center of the molecule. Okay, if you travel from the one end of the molecule and reaches at the center of the molecule, and again in the opposite direction you travel the same distance actually, right, same distance with equal magnitude, then if you encounter the same atom, then such molecules are said to have center of inversion or the center of symmetry. So I already told you, see, if you have the molecule, if your molecule is having the center of symmetry, and you know the all homonuclear diatomic molecules, whether it is H and H, whether it is your N and N, whether it is O and O, okay, and you may your carbon and carbon, they all have the center of symmetry or center of inversion. So whenever your molecule have center of inversion, so you may put G or you may put U as the superscript in the term symbol, okay. And this is actually known as the parity. This center of inversion is basically what? The parity. Okay, so you have to look for the center of inversion to decide the parity. And if you want to decide the what would be the parity, what would be the parity of that term symbol. So for this, actually what you will do, say if you have the multi-electron molecule, so what you will do, you will note the parity of or parity like G or U. The G is the parity, this U is also the parity, right? So the parity of the multi-electron molecule, right, it could be obtained by noting the G or the U value for every electrons in the orbital and then forming their products. And when their products actually give you the results, they will decide the parity. But for this, you should know, if you have the one electron in particular orbital and it is having the parity of the G, okay, G means it is having that particular G, right? That means the G rate. G rate means evenness, that means the center of symmetry, presence of the center of symmetry. And if you have another electron, it is also having that same parity G, so you will note down the parity of that electron, you will note down the parity of that electron, and you form the product of this one, G multiplied by G. So whenever you multiply G with G, you will get the G. That means G rate multiplied by the G rate, you will get the G rate, okay. But you may also have the other combination, say one is having electron is having the parity of U, that means un-G rate, second is also U. So when you multiply un-G rate into un-G rate, again you will get the G rate. So parity would remain the same, very important. But if first is having the G rate parity, second is having un-G rate one, so this will give you the un-G rate. And similarly, if first is the un-G rate and second one is the G rate, again you will get the U for this one, okay, that means the un-G rate. So this is, see guys, it is quite simple actually, right? So see, later I will explain to how we can actually remember this G. So I am giving you the one way actually. Say for example, see right now I am not giving you, in the next slide I will explain all these things actually, okay. So this is how actually you will note down the parity of the each electron present in the orbital, and then you will form the products of that parity, and that will decide the term symbol, okay. Now if I go back and coming here actually, so now you are quite familiar what is this S, what is this 2S plus 1, what is this plus and minus, what is this G and U, and what is this lambda. So this is the term, see this is actually, see, somewhat like that your atomic term symbols which I have discussed in your coordination chemistry part also, okay. So this is actually like that actually, not exactly the same thing, because in that case atomic orbitals was there and atomic orbitals were there, but right now I am having the molecular orbital. So this is all about your homonuclear diatomic molecules. Now you can think in that manner also. You may also have heteronuclear diatomic molecules. Say for example, you are having the heteronuclear diatomic molecules. Heteronuclear diatomics or diatomic molecules. So they may include the various examples. Okay, you may have your lithium fluoride, you may have your hydrogen fluoride, you may have your cyanide, okay, you may have your nitrosyl, you may have your, rather you see the carbonyl you may have, okay, and apart from the carbonyl you may have the HCl molecule also. So various things are there. Now what would be the term symbol in that case? So all things will remain the same, like 2s plus 1, there is no problem in that, lambda is fine, plus and minus sign would also be there. But in the earlier case you have written G and U, but in the present case this G and U, G rate or un-G rate concept would not be there, because your heteronuclear diatomic molecules, they don't have the center of symmetry, right? I is absent. I means center of symmetry, and this center of symmetry is absent in the heteronuclear diatomic molecules. So there is no question of putting G on or U as superscript. So that's why it is omitted from here, and for heteronuclear diatomics you will use this term. Okay, now this is quite fine. Now I am going to explain what is G and what is U, that means the center of symmetry. See, if you are however, if you are the regular viewer of my channel, then there would be no problem in understanding the G rate and the un-G rate term, because I have discussed these terms in my coordination chemistry and a number of times actually, right? But if you are new here, then and you don't know about the parity, so for this actually I have to give you some idea. Okay, so what the idea is actually, so I am giving you in that manner. Say next. Okay, so this diagram, guys, you can focus here, right? So here you can see for this diagram, this is your s orbital, this is your s orbital, and they are doing constructive overlapping in the light of the molecular orbital theory. So they will form the sigma bond. So this is the symmetrical electron cloud, cylindrically symmetrical electron cloud between the two nuclei. This is the nuclei 1, this is the nuclei 2, and this is the positive overlap, right? Whenever you have this formation of this sigma bond, then this would be G rate. I can write, see, I have already written here sigma G, where G stands for the G rate. G rate means presence of the center of symmetry. So what is the meaning of the center of symmetry? If I start from this end, okay, and reaching to the center of the molecule, and then move in the opposite direction to this equal distance, if actually the phase is same. So here you see the phase is same, that means the center of symmetry is there. In that case, I is present. When center of symmetry is present, then your orbital would be G rate. So that's why sigma G is written over there. So you will remember this very important point. Okay, that means G. So what I can do simultaneously, I can write it here actually. I can write it as, right, atomic orbitals parity. So don't confuse here actually, because we are discussing the molecular orbital, but I have written the atomic orbital. See, this is the this is the sake of the understanding. So whenever you have the s atomic orbital, right, this is s atomic orbital. So this is, you can see, this is if you consider this one s atomic orbital, so all along this symmetrical electron cloud in the atomic orbital, if you move, say if you move from here to here, right, so phase is same. If you move from here to here, phase is same, that means I is present. So s orbital is always having the I, so that's why it is this s orbital is always the G rate. S atomic orbital is always the G rate. Okay, and I can write it here as here parity of your bonding molecular orbital. So bonding molecular orbitals parity, right? So whenever SS is combining, so this will also form the sigma bond, and that sigma bond would always be G rate. Okay, this is see how easy this one. Now if I go to here, actually here you can see this is destructive overlapping. Okay, that means the negative sign is there, and when they overlap actually, so there is a node present in it. Okay, so one node is present, that means it is un-G rate one, that means it is not having the center of symmetry. So why it is not having the center of symmetry? You can easily see here. If you move from here to here, positive sign is there, and if you reach to the center of the molecule somewhere here, and if you move in the equal direction again, you will find the negative sign. That means phase is changed here. So that's why if you focus here, I have written sigma U anti-bonding. Okay, so if S bonding sigma G is actually if sigma bonding is G rate, then sigma anti-bonding must be un-G rate. Okay, so I can write it here anti-bonding MOs, anti-bonding MOs or not of parity. So I can write it here as parity. So this could be your, I can write it as sigma anti-bonding, and this would be unG-rayed. See how easy is this one. Now if I focus on the next orbital, say I am having the p orbital here. Okay, so for p orbital, I can tell you actually, say I am giving you here, say this is your px orbital, and this is okay, let me little bit write it or draw it little bit more clearly. Say this is your px orbital, and this is the positive sign here, this is the negative sign. So p orbital is not having center of symmetry, no I, that means no center of symmetry is present. When center of symmetry is not present, the orbital would be unG-rayed. Okay, again I can explain this. This is the negative sign somewhere here. If you move to the center right here, and if you move further back in the opposite direction with the same distance, so you will find the changed phase here. That means no center of symmetry is present. That's why this p orbital is always unG-rayed. Okay, the p orbital is unG-rayed, and when this p orbital is unG-rayed, okay, then definitely when you have this p orbital is forming your pi bond. Okay, I can write it here. If it is forming the pi bond, okay, so this would be your unG-rayed. Pi bonding would be unG-rayed. Okay, then definitely your pi anti-bonding, if I write, this must be G-rayed. So how I can explain this one? You can see here, this is the p orbital. See, this is px I have shown here. See, if I want to draw it little bit more clearly, say this is the px orbital, right? Just like that. Okay, and if you see here, this is the negative sign. If you move here, this is positive sign. So this is unG-rayed one. Okay, and when they are this is unG-rayed, this is also unG-rayed. Okay, and when they combine actually, and if they are forming pi bond, so I can take this example, not that one. I can take this example, right? So this is the p orbital, this is p orbital, right? This I can take. Forget about this one. Okay, I'll come to that because it is forming the sigma bond, because it is the axial overlap. Okay, so I'm not discussing this one. Focus on this one. Say this is the lateral overlap, and when they overlap laterally, so they will form this molecular orbital pi. So here there is no center of symmetry. If you move from here to here, so here is negative sign and here is positive sign. Okay, that means no center of symmetry in that case. Okay, when there is no center of symmetry, obviously it would be unG-rayed. So pi unG-rayed is there. Okay, you can see here I have written pi unG-rayed. That's why pi is unG-rayed. But if you focus here actually, right, this was your actually constructive overlap. They are overlapping with positive sign. Here destructive overlap. Okay, when they overlap, so they are having the center of symmetry. How they are having the center of symmetry? If you move from here and reach to the center of the molecule and move to the opposite direction again, so this is negative again. That means, or from here again also, this is positive, this is positive. So anti-bonding is having the G-rayed system because it is having I in that case. That's why I have written here p orbital when forming the pi molecular orbital. Since p is unG-rayed, so pi bonding will also be unG-rayed, but pi anti-bonding would be G-rayed. That's why I have put it G here. I hope this makes the sense. Okay, and see, whenever you are having the diatomics actually, so you will always encounter with s and p orbital. You will not encounter with the d and f orbital. Okay, so this much of thing is quite enough for you to understand. Okay, so now say to complete the things, I can now quickly write here. Then you may have your d orbital. Okay, and then you may have your g orbital, and then you can write here as g again, and you can write as u again, but there is no need to go for the explanation for this one. Okay, and again for this one you can write it here whenever if it is g and they are forming the bond, so this would be with the g symmetry. Okay, and this would be with the u symmetry, bonding orbitals, and that would be your anti-bonding would be opposite to that of the bonding one. So this would be the unG-rayed and this would be the G-rayed. Okay, and the easy way to remember this one, Gugu, So what you can remember this mimic, actually this mnemonic gugu, okay, and you can write it as here SPDF. So if you remember this this trick, actually SPDF gugu, that means G-rayed, G-rayed, G-rayed for atomic orbitals as well as for their bonding molecular orbitals, but the reverse will be true for the anti-bonding molecular orbitals. Okay, so you can see here, but before actually moving further, I can explain you this one. So actually you can see here, this is the sigma bond is forming actually, right? So this is, they are, because these p orbitals are coming axially, so their axial overlap is happening here. But see, in that case, in the overlapping, axial overlapping, this is the negative sign here, this is also the negative sign here. If you test the center of symmetry in that case, right, so this is negative sign, reach to the center of the molecule, move in the equal direction or equal length to the opposite, in the opposite direction, then you will find negative and negative, that means it is G-rayed. Okay, and I know the, and I already told you, whenever you have the sigma bond, it is always be the G-rayed one. So this much of explanation is must to decide or to know the to determine the molecular term symbol. So this is the theoretical background, which is very, very important. Okay, so now I can give you the sum of the examples, right? And with those examples, actually what you can do, see this is the theoretical background. So what I am doing, because the length of the video is increasing so much, so I am stopping here actually, and in the next lecture I'll explain you how to calculate the this these term symbols for the different molecules. Okay. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, yesterday, that means in my last class, I have discussed all the theoretical background which is must to determine the molecular term symbols for the diatomic molecules. Okay, so today I am going to discuss the problems based on this and the problems which have been asked in the CSIR NET examination as well as in the GATE examinations. Okay, so if you are new here and you are watching this video for the first time, let me remind you what actually I have discussed in my last lectures. Okay, so you see here, this much of thing I have already discussed. You see here, right, this is the review actually. So this formula is used for the determination of the molecular term symbols. I have discussed all the plus minus sign, G and U, S and lambda. I have all discussed in my last lecture, right? If you see, if you haven't seen that video, so it is very important to see that particular video in order to understand this lecture, the problem based on this lecture completely. Okay, so this I have explained, and then you see here I have already give you this the importance of this quantum number, and then I have already discussed you this Greek letters used for the spectroscopic terms, and then I have already discussed this plus and minus sign. All these things I have discussed, what is actually G, what is used with respect to the center of symmetry. And then for the heteronuclear diatomic molecules, I told you then the G-rayed and G-rayed would not be there because they don't have the center of symmetry. Okay, and then I have discussed these things. So up to this point I have completed in my last lecture, and today I am going to discuss the problems based on this. So if you are new here, please watch that particular video. The link is flashing over there, okay, at the top right corner. Okay, now you see here, today I am going to discuss the things here. So first of all, you should remember that point, guys. Whenever you are determining the molecular term symbol for any diatomic molecule, you must know the basic molecular orbital theory. If you don't know the energy order of the molecular orbitals, then you will never be able to determine the correct molecular orbital term symbol. Okay, so this you can see here, I have written here, this is the molecular orbital diagram, and that molecular orbital diagram actually belongs to those molecules which are having the electrons less than or equal to the 14. So this molecular orbital diagram is applicable only for this for those species which are having the electrons, okay, less than or equal to 14. Okay, and in this range, you know what molecules you can have. So in this range, you may have you may include your systems like from hydrogen to nitrogen. Your hydrogen, helium, lithium, beryllium, boron, carbon, okay, nitrogen. So from hydrogen to nitrogen, this actually diagram will follow. And for the better clarity of you, I have already written here actually. See, whenever you have this sigma 1s, so I already told you sigma orbital, whenever the bonding sigma orbitals are there, then their parity would be the G rate. So I can write, see, this is bonding sigma orbital G rate. So anti-bonding would be un-G rate one. This I have told you in the last lecture actually. Okay, and then sigma bonding, this is G rate, sigma anti-bonding un-G rate. Okay, and I already told you pi molecular orbitals bonding one, they are the un-G rate one because they are not having the center of symmetry. Okay, but sigma orbital of any kind, whether they are forming through the s orbital or s or p orbital or p or p orbital, so this is this will always have the G rate symmetry. So sigma 2pz, if you are considering that internuclear axis is the pz one, right? So this sigma 2z will form the, this 2pz will form the sigma bond and it will have the G rate symmetry. And when your pi bondings are un-G rate one, then pi anti-bondings would be the G rate one, and they are actually the doubly degenerate. I already told you in my last lecture that means non-degeneracy is there for the sigma orbitals, but pi orbitals are doubly degenerate. So this is the degeneracy 1, this is degeneracy 2. So for this one you will use the +1, for this one you will use the -1. So I can write it here. If you have the electron here, so for this you will use the +1, for this you will use the -1, but for all sigma there would be no such thing actually. You will use the 0 all the time. Okay, this is important guys, this is very important. Remember this point. So this is +1, this is -1. Okay, this is 0. See, I have put it the +1 and -1 in that manner, but we cannot tell exactly actually whether this one is the -1 or this one is the +1 actually, right? But this is the way of doing this. Okay, and for this actually energy order I have drawn the molecular orbital diagram. Now let us discuss actually the molecular term symbols of the some molecules. Okay, so I am going for nitrogen actually. Okay, so what I am doing, I am determining for nitrogen. So I am writing here nitrogen N2. So nitrogen is having the atomic number of 7 plus 7, that means you are having the 14 electrons. So your duty is what? To fill the 14 electrons. So how you will fill the 14 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Okay, it simply means 2 electrons are here. Sorry, I can use different colors so that it can actually clearly visible. So this is 2 to 4 to 6 to 8 to 10 to 12 to 14. Okay, and in that case, see guys, all the electrons are actually paired in that case. Okay, now you know what is the formula. Since this is the homonuclear diatomic molecule, the formula for the molecular term symbol is what? Lambda 2s plus 1, and then you are having that G rate or un-G rate or plus or minus sign. So here you can focus your last 2 electrons. Sorry, in my last lecture I actually told you that I told you that the electrons actually must be unpaired. So it is not like that. Please correct it. Okay, it is not like that. Okay, so in that case you see electrons, where the electrons are there in the sigma orbital. Okay, you can see here this is sigma orbital, and when the electrons are there in the sigma orbital, that means there is no net angular momentum in that case, and the resultant angular momentum value would be 0. So in that case your lambda equals to 0, and please recall, for lambda equals to 0 you use this term sigma, for lambda equals to 1 you use pi, for lambda equals to 2 you use delta, for lambda equals to 3 you use phi. Okay, that means you are using the sigma. So first thing you have identified, for this nitrogen molecule you will use this lambda. Okay, now you have to calculate this 2s plus 1, right, spin multiplicity. And for this spin multiplicity, say you are clearly observing here there are 2 electrons which are paired. For the pair electron, if you want to calculate the s, so s what? Plus half minus half. So plus half minus half would give you the 0. That means 2s plus 1, that means 2s plus 1. This will give you 2 into 0 plus 1, that is 1. So spin multiplicity is 1. So in place of this 2s plus 1 you can write 1. Okay, and you know where your electron is, where your last valence electrons are there. Your valence electrons are there in this pz orbital, which are the G-rayed ones. So symmetry is the G-rayed. Okay, for this the symmetry is the G-rayed. When the symmetry is the G-rayed, you can straightforward write G. And I already told you, whenever, remember, please remember this point, whenever you are having this sigma G, you will always put positive, because in that case the sign of the wave function would be unchanged on the operation with sigma V. That means if you put the sigma V in the wave function, then the sign will not be changed. So you will put positive here. So for nitrogen molecule, not 1 actually, very sorry, not 1. For nitrogen molecule, your molecular term symbol would be 1 sigma G positive. I hope this example is quite clear to you and there is no problem in understanding this thing. Okay, so this is how actually you can calculate. This is the stepwise mechanism. So now if this is clear to you, then I am going to discuss your another molecule, or say ion. What I can do now, I am discussing N2 positive. Say if it is forming the N2 positive, so before going into the N2 positive, I have to remove all the things which I have actually written here. So I am deleting all these. Okay. See, if you have the N2 positive, that means 1 electron is less. So you have to remove 1 electron. So you will remove 1 electron from here. So the moment you will remove 1 electron, so you will remove 1 from here and you will write only 1. This is how you can write. And that electron would have, see in the pz orbital, this electron you can show in that manner with the positive spin, okay. And please remember how you calculate actually your this lambda. So I already told you, your electron is present in the sigma orbital. Whenever your electron is present in the sigma orbital, that means there is no net resultant angular momentum, right? Orbital angular momentum, there would be no net angular momentum. So this would be 0, and for this lambda equals to 0, you will use this Greek letter sigma. So you can put again very easily that sign sigma here. Okay, and again the same thing you can see now. It's easy for you because your electron is present in the G-rayed. Okay, this is sigma G, and whenever sigma G is there, I already told you the method. Whenever the sigma G is there, you will write sigma G, and for sigma G you will always put positive sign. Okay, now you have to calculate the S. So you are having 1 electron which is having the plus half of the sign. So you can calculate 2s plus 1. So 2 into half plus 1 equals to 2. That means spin multiplicity, that means 2s plus 1 is actually 2. So you can write it here 2. So for N2 positive, your molecular term symbol was this one. While in case of your nitrogen only, you are having 1 here. You were having the 1 here. I hope this is clear to you. Now again I am changing the system, and now I am going to give you. So please correct this one. If you put positive here, then this would be 6 and this would be 13. I forgot to do this thing actually, but please remember. Okay, so now moving to the next one. Okay, now I am going to discuss your say N2 negative. I am discussing N2 negative. That means 1 extra electron. That means 7 plus 8 equals to 15. Now you are having the 15 electrons. So now you have to fill the 15 electrons. So this is 2 to 4 to 6 to 8 to 10 to 12 to 14, and this is the 15th one. This will come here actually. Okay, so how you do that in that case? That this is again quite simple here. Where your electron is, right? You have to calculate this one. So I have to actually change this thing from here also. This would be 2, and this would have 1 electron. Okay, and see here in that case, whenever you are doing this one, so where your electron is, your electron is in the pi orbital. Okay, when your electron is on the pi orbital, okay, so in that case, see what is the value of this this m actually. See, this is W degenerate, this is WG degenerate. So M for this one is +1 and for this M is -1, but your electron is present is M plus 1. Okay, so that means if you calculate the total value of this will give you the 1. That means your lambda is 1. So whenever your lambda is 1, you can see here your lambda is 1. That means you will use pi for this one. So you will put pi here because this lambda is giving you that pi. Okay, so first step you have completed. Now since actually this is the pi orbital, right, so there is no need to put that positive and negative sign. Remember that positive and negative sign is only for sigma orbital, your sigma type of letter actually. When pi delta phi is there, so there is no need to put the plus and minus sign, so you will not put the plus and the minus sign. And you see the electron, this is present in the G rate. Okay, so you will write G here. Why? Because the symmetry is the G rate. You see here, because the symmetry is the G rate, so you can write it G rate here. Now you have to calculate the spin multiplicity. So for the spin multiplicity, again you will do 2s plus 1. Okay, so whenever you are having the 2s plus 1, that means 2, and this electron, you can see this electron which is there, actually it is having the positive half. So what you can do, you can write 2 plus half plus 1, that will give you 2. So that means 2 pi g, the term symbol for this N2 negative is your 2 pi g. So this is actually very, very important, which you should know actually. Okay, so term symbol would be this one, so 2 pi g. There is no problem in that. But see guys, you may argue that why you are selecting this molecular term symbol, because you can see you may have other thing also. You may have 1 also here in that case. Okay, but I am not going to discuss that point. Please remember, so I am actually doing the correct things actually. I do not want to confuse you actually to put the different signs here, but this is how you can write it, right? So this is for your nitrogen molecule. So if this is clear to you, so let us take another example, or say I can take some other example, say carbon. I am doing for carbon right now. Okay, say I am deleting all these things from here. All these things I am deleting, no problem, and all these things. Okay, this I have removed from here, and now I am doing for your carbon, so I am deleting for this also. And then say you are having the carbons, you are going to form the C2. So C2 means your 2 carbon atoms, so 6 plus 6, that is 12. That means 12 electrons are there. So if you want to know the electronic configuration, or if you want to fill the electrons in it, so this is 1, 2, 3, 4, 5, 6. So this is the electronic configuration. So 6, right, and 7, 8, 9, 10, 11, 12. Okay, so these 12 electrons are there. So guys, please remember this point. If you do not want to draw this particular diagram every now and then, so you have to remember this sequence. If you know this sequence, then there is no need to draw this one. Okay, so now I am going for this carbon. So where is your actually last electrons? Your electrons are there in the pi orbitals. Okay, so I am drawing this here. Please remember, say this is one pi orbital, this is another pi orbital. I can write it as pi 2p because they are the bonding one, so they are the ungirate. So pi 2p ungirate. So for this is +1, for this is -1. Okay, this is important, this is very, very important, and all are having the electrons 1, 2, 3, 4. See, I am doing for these electrons. I am doing only for these electrons. Now you have to determine the delta. Lambda. See, this lambda is nothing but it is the absolute. This is the absolute value of this ml. Okay. So how you can write it as? See, your first electron which is present here, it is having the value of the +1. Your second electron is also having the value of the +1. So straightforward you can write it here, +1, +1. while your next electrons here, this is -1, this is -1. So again you can write it here, -1 -1, that will give you the 0. That means lambda is 0, and you know when lambda is 0, what letter you will use? You will use this sigma. So you will write sigma over there. So there is no problem in that. Okay, now all electrons are paired in that case. You see the all electrons are paired, these electrons are paired, that means S is 0. So if you want to calculate the 2s plus 1, 2s plus 1, that will give you 2 into 0 plus 1 equals to 1, that means S is 1. Okay, when S is 1, so simply you can write it as 1 here. Okay, and where you are, see, now you have to decide the parity. Now you can go for the parity. For parity, I already told you, you are, see, this is actually the unzeroed one, this is also the unzeroed one. So if you write the one electron like that, another electron like that, one electron like that, another electron like that, so what you do, write unzeroed for this one, multiplied unzeroed for this one, because both are present in the unzeroed orbital, and unzeroed for this one and unzeroed for this one. So if you multiply this unzeroed to unzeroed, that will give you the zeroed. That will give you the zeroed. Similarly, that will also give you the zeroed, and finally this zeroed into this zeroed, that will give you the zeroed again. So you can write G here, and whenever you have the sigma G, then you will always put plus sign over there. So the molecular term symbol for your carbon is this one, right? By using the same technique, you can actually determine for your C2 positive, you can also determine for C2 negative. So this much of explanation I think is sufficient to actually explain the things for your homonuclear diatomic molecules up to total count of electrons equals to or less than the 14. Okay, now moving to the next one. Right guys, you can see this molecular orbital diagram, and this molecular orbital diagram is applicable for the system, for the species which are having the electrons greater than 14. Okay, so whenever you have the electrons greater than 14, then you will follow this particular diagram, and in that diagram the only thing is that this order has changed. In the earlier case, pi 2p and pi 2p were of lower energy and sigma was of high energy. See, please check. You see here that pi 2p, they are having the lower energy, and sigma 2p is having the higher energy for your actually the system which are having the electron less than or equal to 14. But whenever you have the electron greater than the 14, okay, then this would be actually reversed. That means 2p will come down and they will go up. The only thing actually which you need to change. So this actually I have changed here. Rest other things will remain the same. So in energy order also, guys, you can see here what I actually do. In that case, sigma 2p is having the lower energy, while your pi 2px are having the higher energy. All things are same actually, right? Now if you say we can take another example for this one, and to explain this one I am taking fluorine. Okay, I am taking the fluorine molecule F2. Okay, so if you are taking the F2, that means 9 plus 9, 18. That means 18 electrons are there. That means you have to fill the 18 electrons in it. So how you fill the 18 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is how I can write. Okay, there is no problem. See guys, I am only filling the molecular orbitals. I am not focusing on the atomic orbitals. In the previous examples, I have also not focused actually on the atomic orbitals. So don't think in that manner. There are nothing in it. So their electrons are there, but I haven't drawn. Okay, so this thing is there. Now the term symbol actually. Okay, so for the term symbol, you know, you will use this formula 2s plus 1 lambda plus or minus zeroed or unzeroed. Okay, now first of all you fill the electrons here also. So you can write it here 2 to 4 to 6 to 8 9 10 11 12 13 14, right, 15 16 17 18. So you are having the electrons here. Okay, and again if I draw here this is having the 2 electrons, this is also having the 2 electrons, okay, and say this one is actually pi 2p, because they are the anti-bonding one. Please remember, they are the anti-bonding one, so they are the G-rayed. Please remember this one. So I am writing G here for the G-rayed. Again I am writing the 2p G-rayed, because electrons are present in the G-rayed orbital. Now if you want to determine the absolute value of this angular momentum, that means your lambda, how you can calculate? You know, for this pi the value is +1, for this pi the value is the -1. Okay, so for first electron is +1, for second electron is also +1, for third electron is -1, and the fourth electron is -1. That will give you the 0, and when lambda equals to 0 you use this sign sigma. For this fluorine you will use sigma. Okay, and now you determine 2s plus 1. Since all electrons are paired, so their spin gets cancelled, that means the s value is 0. Okay, so you can write it as 2 into 0 plus 1 equals to 1. So you can write it 1 here, and see the G-rayed is there, so you can write it G here, and I already told you, whenever you have this sigma G, you will always put plus sign over there, so you can write positive over there. So this is how you can draw, or you can determine the molecular term symbol for the fluorine. I hope this is quite clear to you. So this example is quite enough. You can do practice by your own by actually drawing the diagram for the others also. I hope this is clear to you. Now moving to the next. Okay, now see guys, I have moved from your homonuclear diatomic molecules to the heteronuclear diatomic molecules. Okay, and when it comes to the heteronuclear diatomic molecules, that mean in that case G-rayed or un-G-rayed would not be there, but this problem is quite different from that problem, and this problem has been asked in the CSIR NET 2018 examination. See, the characters of the LUMO in the cyanide and the O2 respectively are, so these 4 combinations are there. So for this you have to have an idea about the HOMO and the LUMO. Okay, so what are the HOMO and the LUMO? See, HOMO is highest occupied molecular orbital. See, that's why, see guys, I already told you, it is impossible for you to determine the correct term symbol, right, or correct characters for any orbital if you don't know how to draw the molecular orbital diagram. So it is mandatory for you to actually learn the molecular orbital diagram, especially for the heteronuclear diatomic molecules. You cannot apply this, you cannot apply that system. Say for example, this is CN, this has been asked for the CN negative, carbon is 6, okay, nitrogen is 7, 1 extra electron, that means 14 electrons. If you follow, see, if you see, okay, it is 14 electrons, so you will fill the electron. If you want to fill the electron in the nitrogen, as you have filled in the nitrogen molecular orbital diagram, this may give you, sometimes this may give you the correct answer, but most of the time you will get the wrong answer in that case. That's why it is my personal advice to you, please learn all the molecular orbital diagrams before solving the problems. Okay, so I am removing this one. This was for your explanation only. Now see, this is actually HOMO. Why HOMO? Because this is the filled molecular orbital with the 2 electrons. HOMO stands for the highest occupied molecular orbital. I have drawn a video on to identify the HOMO and the LUMO, right, for the diene system, okay, and polyene system, not diene only, but also for the polyene system. If you haven't seen that particular video, it's a very beautiful video. You will actually see, if you have any doubt in understanding the HOMO and the LUMO, after watching that video you will clearly know actually how to decide the HOMO and the LUMO. So here is the link at the right top corner, it is flashing. Go through that particular video actually, right, to understand all the things. But right now this is the HOMO, highest occupied molecular orbital. Then immediately after that you are having the LUMO. This is the LUMO of cyanide. This is the LUMO of the cyanide. Okay, when this is the LUMO of the cyanide, then what is given here, you see here, it is sigma. So whenever you are having the sigma, see, this is forming 3 sigma orbital, and this one is here LUMO. See, the question is on the LUMO. So LUMO is the pi anti-bonding. Okay, and I already told you pi bondings are un-G-rayed, but pi anti-bondings are the G-rayed one. So this actually, right, that this is what actually, this is pi g. That LUMO is having the symmetry of the pi g. So check whether you are, see, this cannot be your answer. This cannot be your answer because it is sigma g, but electron is not in the sigma. This cannot be your answer because it is pi ungerade, but your answer is what? Pi antibonding, that means pi gerade. Third option is having the pi gerade, so this could be the correct answer, and it is not having, see, this is sigma u, this cannot be your answer. So if you know this much of thing, then you can blindly mark this as the correct answer. There is no need to check or investigate the oxygen further. So this is the one way, okay. And if you want to know the what would be the LUMO for this actually oxygen, so you can go back. So this was your oxygen, so this was your LUMO. For oxygen, this was your LUMO. This is LUMO, and that LUMO is actually the sigma antibonding 2p, and you know the sigma antibonding 2p is ungerade. You see here it is ungerade one. So for oxygen it would be ungerade. So you can clearly from here sigma u. So this is the correct answer. So this question was quite easy, but you have to have an idea about the molecular orbital diagram for the heteronuclear molecules. Okay, now moving to the next problem. Okay guys, this is the HF molecule, right? I am giving you another example, very beautiful example, you can check here. This is your HF molecule, and in that HF molecule, okay, so you want to determine the wave function. Okay, so I can write it here. HF, it simply means 1 for hydrogen, 9 for this one, 10 electrons are there. But you cannot follow that diagram which you have drawn for the nitrogen case. Okay, this would give you the wrong result, completely wrong result. Okay, so now this is the molecular orbital diagram. As I already told you, you should know the molecular orbital diagrams, and you have to fill the electrons in it, right? So for 10 electrons, you have filled electrons here. Okay, see, this is 2 to 4 to 6 to 8. Okay, 8 electrons are there. Rest 2 electrons actually your 1s electrons, which actually they haven't shown here. So 1s electrons are there, but they haven't shown. But don't worry, there is this will not make any difference. Now you have to calculate the term symbol. So how you will get the term symbol? So you are having this species. So you quickly what you do, you write here these two species and put the electrons into it, 2 to 4. Since they are the, see, this is 2px, this is also 2px, and they are doubly degenerate, that means they are the pi 1, because sigma orbitals are non-degenerate. So for this one the value is +1, for this the -1. If you want to calculate that resultant orbital angular momentum, that will give you that quantum number lambda. So this will give you what? +1, +1, -1, -1, that will give you the 0, and when it is 0 you will use the term sigma. So for this you will write sigma here. Now you have to calculate 2s plus 1. So all electrons are paired. See, that means if you want to know their spin, that means +½ then again +½ -½ and again -½ that will give you the 0. So this will give you 2 into 0 plus 1 equals to 1. So spin multiplicity is 1. There is no problem in that. Now if you want to know the parity, parity means determination of parity, that means the center of symmetry. So this was actually, you see this px, they are they're actually they haven't shown that G or U here. Why they haven't shown the G and U here? Since it is the heteronuclear diatomic molecules, then I is absent. Okay, when I is absent, so there is no question of U and G in that case. Please remember that point. For any heteronuclear diatomic molecules, there is no question of G and U. If you write G or U somewhere here, then you will end up with the wrong answer. So please remove this point. Please remove this point. Now the question is that what you have to put here actually, right? Plus or minus. So I already told you, when 2s plus 1 equals to 1, then you will put the plus sign over there. And whenever you are 2s plus 1 equals to 3, then you will put -1 here. But in that case, 2s plus 1 equals to 1, that means you have to put plus sign. So this is plus, So this is the molecular term symbol of HF molecule, 1 sigma plus. This is the point which is very, very important, and this point actually 1 or 3, this 2s plus 1 equal to 1, 2s plus 1 equal to 3, this I have discussed in my last class. This is very important, very, very important, which you should know. If you have followed my lectures properly, then there will be no problem in understanding these things. Okay, I hope there is no problem in that. Now moving to the next problem. Not next problem, this is the, okay, see guys, I am discussing the molecular orbital diagram for this carbonyl. This is this CO is very, very important, guys. Please remember, this CO is very, very important, okay, and because this is the special case. And again you see, if you, again I am telling you that thing here, if you have the CO, then 6 plus 8 electrons of carbon, electrons and of oxygen, that will give the 14. And if you follow that nitrogen molecular orbital diagram, this will give you the wrong result. For this you have to know the correct molecular orbital diagram of the carbonyl. So this is the correct molecular orbital diagram which I have shown you here. Now if you want to calculate the molecular term symbol for this one, then how you will go actually in that case. So your electrons, where your electrons are, so I can write it your electron here. Okay, this is sigma anti-bonding 2s, and sigma anti-bonding is always ungerade. Please remember, this is also ungerade one, but there is no question of the gerade or ungerade. Why? Because this is the heteronuclear diatomic molecule, so you not need to worry about the parity. You will not write this U here. Okay, so there is no question of the gerade or ungerade, but straightforward you can put the 2 electrons over there. And you know, whenever the electrons are there in the sigma orbital, that means there is no net orbital angular momentum. That means this would be 0 and this would be 0. That means you will have this Greek letter sigma. For this carbonyl you will put sigma here, and then you will calculate the 2s plus 1. Both electrons are paired, that means plus half and minus half, that will give you the 0. So you will write 2 into 0 plus 1, that means 1. So you will write 1 here. There is no problem in that, and there is no need to put G and U. Whenever you are not having the G and U, then how you decide actually where to put positive and negative. So I already told you, whenever 2s plus 1 equals to 1, you put plus sign, and whenever you have 2s plus 1 equals to 3, you will put the minus sign. So you will put plus sign over there. So this is again, you see the term symbol, molecular term symbol for the carbonyl. So this actually this is very, very important. Now moving to the next problem, which would be my last problem in the lecture. Okay, so this question has been asked in the CSIR Net 2016 examination, and it's a quite good problem. And you see here what they have asked: the highest molecular orbital for an excited electronic configuration of oxygen molecule. So guys, however, I haven't discussed the excited states of the molecule, but in the next lecture I will cover the excited term symbols for the excited states and how to determine the ground state, right? And the first excited state and the second is the excited state of the molecule, and then the how many kinds of the transitions actually allowed or the disallowed transition. This I will discuss in the next lecture. This would be my that would be my last lecture on the molecular term symbol. Okay, but for this electronic configuration I can explain the problem how you can go for this one. Say you have been given this 1 pi G. Okay, that means it is this is already given excited state. It is excited state. Okay, see, if you have followed that oxygen molecular orbit diagram, then you may end up with the confusion that why G is there, because pi bonding is actually ungerade one. Remember, this is not the ground state, this is the excited state which is already written here, and that excited state concept I will explain in my last lecture. But right now you can focus on the parameters which are given in the question itself. This is 3 sigma U and 1 electron is here. Okay, so what are the possibilities? Okay, what are the possibilities? So in that case actually I can give you the possibilities how you can write. Say first point you may take in that first point you may write in that case, say this is pi G, and that pi G is having this electron and equals to pi G which is having nothing. Okay, and then you are having your sigma U, and that sigma U may have this configuration. Okay, but another possibility is also there, that you are having the pi G and it is having this spin, that means this positive sign, and here is nothing in it, and in that case this is sigma u, and it is having the anti-parallel spin. And remember, please remember this point, for this one m1 value is +1, for this m1 value is -1, and for sigma is 0. Again, for this +1, this is -1, this is 0. So if you want to go, if you want to explain this part A actually, so I am going for this A actually. So your electrons are present in sigma and pi. So how you can determine? Say for this one, it is the value is the +1. So if you go for the lambda, that means +1, and no electron is there in that case, so you cannot put minus here, because to put minus here you have to have an electron here, but the electron is not present here, it is the excited state, and for this sigma it is 0. So you can write it as +0, that will give you the 1. So whenever this value is 1, I already told you, then you will use the pi. Okay, the Greek letter pi would be used. So for this A, you will use the pi. Okay, now you have to calculate the spin, 2s plus 1. So for 2s plus 1, see, these two electrons are paired, not paired, actually unpaired, so both having the plus spin. So you can write +12 and +12, that will give you the 1. So you can write 2 into 1 plus 1 equals to 3. So this is 3 pi. Okay, there is no problem in that. Okay, so this is the terms. There is no question of the u and g and plus and minus sign in that case. But if you follow this one, that means this you don't have this symbol here. That means this excited state is not the correct excited state which I have drawn. So obviously I have to move further for this one. So now I am moving for the B. So for this B, I have to remove all these things from here. Okay, now I am solving for the B and calculating the lambda. So I can write +1, then +0 equals to 1. So whenever this one, you are using the pi, so again you will use the pi. There is no problem in that. Okay, so then you calculate 2s plus 1 multiplicity. So in that case, see, these electrons are paired. So first is +12 and second is -12. That will give you the 0. That means 2 into 0 plus 1 equals to 1. That means 1 pi. So this is the correct excited state which is given here. So your answer would be A in that case. So this is how you can determine the answer. So these see, various problems have been asked in the previous year CSIR NET GATE examination from this particular topic. Okay, since the length of the video has increased so much, so I cannot explain that excited state concept and the types of the electronic transitions, right? Laporte forbidden and here C spin allowed and all these things. So all these things I will cover in my next lecture. So if you have seen all these two lectures, please follow the coming lecture. Tomorrow I will upload that particular lecture also, and it is very, very important for your examinations also. That's it for today, guys. So thank you very much. Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss the excited states present in the diatomic molecules, and then we will see the types of the transitions which may be there in your diatomic molecules. Okay, and then we will check the conditions, which transitions are allowed and which transitions are not allowed. Okay, so before going into the details of the today's lecture, let us recollect what we have done so far in the last two lectures. Okay, so if I go back, right, so I have started from here actually, and I already told you these see, when you do this, when you calculate the molecular term symbols for your molecules, right? So why it is necessary actually to determine, not calculate, to determine the molecular term symbols. As I already told you, these diatomic molecules generally have a very large number of the excited states. Okay, so and each excited state is generally recognized by its own term symbol. Okay, this concept actually I have told you, and today we will see the importance of these term symbols for the different excited states and how we can recognize that certain transitions are allowed and while certain are not allowed, depending upon the different types of the rules, right, which are there to actually decide the molecular transitions, allowed or the forbidden molecular transitions. Okay, so see, if you have seen the last two lectures, then it would be very, very easy for you to understand But if you are new here and watching this particular video for the first time, it's my suggestion to you, please watch previous two lectures actually, right, which is given in the playlist of molecular term symbols in the tetrahedron chemistry classes. Okay, so this was the situation, and then I have given you the rules. Okay, and based on the rules, then I have calculated, I have determined the molecular term symbols for the different species. Okay, and these are all the things actually which I have explained. These are the molecular orbital diagrams which are must to actually designate the term symbols for any ground state or the excited state. Okay, this was the situation. This much of things I have discussed in the first lecture, and then in the second lecture I have explained all these things, like your heteronuclear diatomic molecules for also I have calculated these molecular term symbols. Okay, this was the case of your carbon monoxide, and this was the CSIR net problem which I have discussed. Okay, and now in the today's class, excited states and the transitions in the diatomic molecules. Okay, as I already told you, these may have the very large number of the excited state. So let us go back actually to check the excited states of the molecules. Okay, guys. So this you have been given that this carbonyl, right? This is CO, and this CO is having this particular molecular term symbol which you are watching here, which I have explained in the last term, in the last turn actually, right? So what can happen if you have the excited state of this carbonyl? Okay, so there may be the large number of the excited states, but I am going to discuss only one or two excited states, only one excited state for this one, and depending upon the electronic configuration given in the question, you can actually determine the excited state. Okay, so let us remove all these things. Okay, let us remove all these things, and now we'll see how we can go for the excited state. So I'm writing CO and putting a star over there, which simply means it is the excited state, and there may be the possibility of the two kinds of the excited state. So the first possibility of the excited state is just like that. Your electron, right, your one of the electron which is present on the sigma anti-bonding molecular orbital, it may jump either to this 2px orbital or to the 2py orbital. Okay, this can happen actually. So what I am doing actually, I am promoting this one electron from the anti-bonding molecular orbital sigma to the this 2px orbital. Okay, I am doing this one. So this would be the first case. So if I draw the electronic configuration now, what will happen? This will have only one electron now. Okay, and one I have promoted to this 2px orbital with the parallel spin, right? This is the excited state configuration. So if you write the configuration for this one, so how you can write, this would be sigma 2s anti-bonding. Now this will carry only one electron, and obviously its energy is less, and then you are having pi 2px anti-bonding molecular orbital, and in this you are also having one electron, and this would be equal to that pi 2py anti-bonding, and this is having no electron. Okay, because I have promoted only one electron, so this 2py would remain empty. So now if you want to calculate the term symbols for this one, for this actually there is no orbital angular momentum, so for this you will put 0. This I have explained in my previous lectures also, and since this because this sigma orbitals are actually non-degenerate, by rest your pi, delta and phi, they are the doubly degenerate. So it is the doubly degenerate, and if you calculate the orbital angular momentum for this one, so this px can have +1 value and this can have the -1 value. However, it is difficult to designate which one is the +1 and which one is the -1. Okay, so this is the configuration. Now I am determining the term symbol for this excited state. So number one, determination of this quantum number, that means delta determination. Okay, this I have already told you, this is a net orbital angular momentum. Okay, and for this see uh, this sigma anti-bonding is having one electron, and the value for this is 0. So what you will do, you will write 0 for this one. This is your m1 value, rather you can say this is your m1 value. Then plus your next electron is present in the pi, and pi 2px antibonding, so it will have the value of the +1. So what you will do, you will write the +1 here, say this is your m2. If you couple them, right, and then you will have the net value of the 1. And you know, when this value is 1, it simply means your spectroscopic term for this would be pi. Okay, this I already told you. If you recollect, actually, if lambda is 0, then it would be your sigma, and if your lambda is 1, then this would be pi. If it is 2, then it is your delta, and if it is 3, then it is phi, and so on. Okay, so for 1 it would be actually pi, so I have written pi here. Okay, there is no problem in that. Now in the second case, you will determine the spin multiplicity, so that would be 2s plus 1, and this would give you that means 2 multiplied by the spin of these two electrons. So this will have plus half, this will also have plus half. You see, both have the parallel spins, right? So this will also have the plus half, and this will also have the plus half value. So this plus half and plus half, it will make 1, 2s plus 1, that will give you 3. So it means spin multiplicity is 3. So the term symbol would become, so I can write term symbol. So that term symbol would be pi, and there is the spin multiplicity. Since it is a heteronuclear diatomic molecule, so there is no need to put the G-rayed or unG-rayed, because they are not having these heteronuclear diatomic molecules are not having the center of symmetry. And since this is a pi term, so there is no need to put the sign of the wave function with respect to the sigma v. So this is the case when you have promoted one electron from here to here. So I hope you have noted down this thing. Now you may have another situation, then say you may have another situation. Let us check that situation also. So what I am doing, I am removing all these things. I don't want all these. I hope you have noted down, or you have taken the screenshot of this. Okay, now I am removing all these things. Now what I am doing, I am promoting one of the electron from here to this px actually, and now I am giving the inverted spin to it. Okay, this is another excited state possible. So like this, you may have the large number of the excited state for which you can determine the your term symbols, molecular term symbols. Okay, so for this again I am doing the same. First case I am determining, in the first case I am determining your lambda. Okay, so that lambda would be equals to 0 plus 1. Again it will give you the 1. When lambda value is 1, it simply means this term symbol would be the pi. And if you calculate the spin multiplicity, 2s plus 1, that will give you 2 multiplied by plus half minus half. Okay, why plus half minus half? Because this is having the plus half spin, and this one is having minus half spin. Because it is anti-clockwise, it is clockwise. Okay, and if you solve this value, right, then plus 1 you will write. Okay, then that will give you the 1. So your term symbol would be pi 1 in that case. Okay, so if you want to know the energy order for this one, so you will get 3 pi would have the lower energy, and this will have the higher energy. And you know, ground state, you are already having that ground state electronic molecular term symbol, that was your 1, that's positive. Okay, so this is the energy order of the different term symbols for the ground state as well as for the excited state. I hope this makes the sense and you understood the thing. Now let us check one more thing. Go back. If I go back, what is the, so if this is your HF molecule, and if you want to determine the molecular term symbol for the HF molecule, so it's my request to please note down the molecular term symbol of normal HF, right? That means it is in the ground state, then it is having the molecular term symbol of sigma 1 positive. Okay, I'm removing all these things. Okay,
fine, I have removed all these things. And now what I am doing, I am promoting the electron. So how I can promote the electron? So what I am doing, one of the electron which are present in this non-bonding set. So this is your non-bonding set. I am going to promote one of the electron from here to at the top position. Okay, so the configuration would become just like that. Right, only one electron it is having. Okay, and I have promoted one electron from here to here, and I am giving you I am giving the same spin actually for this one. Okay, so spin for this one is plus half, and for this is also plus half. Okay, when this happens actually, then you can go for the excited state configuration. So I am writing here HF excited state. So I am putting a star for this excited state. Okay, and configuration would become just like that: sigma 1, which is having the 2 electrons, having lower energy. Then your sigma 2, it is also having the 2 electrons, then another lower energy. And then you will have your non-bonding electrons, that is Nb, and it would be the pi type. And from here now you will have only 3 electrons, right? You see 1, 2 and 3 electrons. And then you have promoted 1 electron from here to your sigma antibonding, which is of sp type. Okay, and you are having 1 electron over there. Okay, so you know your last electron is in the s orbital. Basically it is sp hybridized, but it is considered as the s orbital. So for this actually the value of your orbital net orbital angular momentum would be 0. Okay, this you should remember. And for this one, if I draw the configuration just like that, so this was having 2 electrons. Okay, and it is having the plus 1, and it is having the value of the minus 1, having 1 electron only. So this is the configuration of this. Okay, now if you want to calculate first thing, that is that quantum number, net orbital angular momentum, that is lambda, that would be plus 1 plus 1 minus 1 plus 0, that will give you the 1. So how it has happened, it had happened actually, you see, plus 1 I have put it for this electron, that means for this electron. Then next plus 1 I have put it for this electron, because both having the plus 1, this pi actually orbital is having the plus 1 value, and this one is having the minus 1, and this is the 0. This will give you the value of 1. And you know, when your lambda is 1, simply you will have your pi symbol. Okay, now if you go for the spin multiplicity, 2s plus 1, that will give you 2. Okay, multiplied by plus half, because both are having the same spin of the plus half. So if you write plus 1 here, that will give you the 3. Okay, then what would be your term symbol? Term symbol would be 3 pi for this excited state. So see how easy is this to actually determine the molecular term symbols for the excited states. I hope this thing is now quite clear to you. Now I am going to explain you another thing. Let us check what I have. So this we have done, this we have done, this I have already explained to you. Now you can see this here, if this is quite clear to you. So these are the 3 different forms of the oxygen. So this is the molecular or the orbital diagram for this one, right? This is for oxygen actually, right here. And let us check which one is for oxygen. Sorry, this one is for oxygen molecule, the extreme. What I am doing, I can write here, this is for O2 molecule. Okay, and after that you are having this O2 triplet. This is O2 triplet, and this one is for O2 singlet. So this oxygen molecule can have various excited states, and the most important excited states are the singlet and the triplet state. So in the triplet state, basically you will have the 2 unpaired electron. It is paramagnetic, right? If you do the electron spin resonance spectroscopy for this one, then you will get the signal. And here you see in the singlet state, both electrons are paired, and How actually these names singlet and triplets are given to you, I have already explained in my some of the previous lectures actually, right? You can see I have explained this term various times, but I'm not going to discuss that thing again, because my aim to determine the molecular term symbols for these states, right? So these diagram actually you should uh, remember, you should memorize actually, right? So see, for molecular oxygen, I have already done in the last lecture how actually you determine the molecular term symbol for this one. So I'm not going to actually determine the molecular term symbol for this one. So basically it is not quite clear here, so I can write here, this is actually your 3 sigma g rate with negative sign. Okay, so this was the case. You can determine by using the rule, but I am more focused on your excited state. So first of all, I am going to discuss the molecular term symbol for this your singlet state. Okay, so in singlet state, if you determine that value of the lambda, so what it will give you, it will give you +1 and +1, that will give you the 2. Okay, this is something very very important. Okay, because you see your electrons are having, both electrons are in this orbital actually. Okay, in this orbital, and it is actually p orbital, right? And then if you go for your say spin multi, see, if it is 2, right? If it is 2, it simply means, that mean you will use lambda. Okay, sorry, delta, not lambda, very sorry, it is delta. This was the first case. In the second case, if you want to determine the spin multiplicity, that will give you the 2s plus 1, so that is 2. And you see here, both electrons are paired, plus half and the minus half. So what you can do, multiply it by plus half minus half plus 1, that will give you the 1. 2s plus 1 is 0, right? Just like that. And after that, you can determine the parity, because this oxygen molecule is homonuclear diatomic molecules. So you have to decide whether you will put G or U as the subscript along with your delta. So how you can determine the subscript, you see here, because you see this actually, this orbital where you are having this electron actually, right? This is G rate actually, right? So you can put 1 G for the first electron, second G for another electron. Okay, so it will give you G multiplied by G, that is equals to G. Okay, when it is G, then in that case you can write delta G1. So this is the molecular term symbol. Okay, and I hope this is clear to you, which I have explained here. So there is no need to put sign plus or minus, because plus and minus sign we put only for your spectroscopic term sigma. Okay, this is important. Oh, I hope this is clear to you. Okay, one delta G. Now I can explain the second thing, which is your triplet state. So I'm going for your triplet state. So how you can determine for this triplet state? Again, it is quite easy. Go for the delta, that will give you the +1 and -1. Okay, and you know why it is +1 and the -1? This I hope you know. See, for this you will have the value of the +1, and for this you will have the value of the -1, while in the earlier case for both you were having the +1, that's why you got the value of the 2. Okay, so +1 and the -1, and if you subtract this will give you the value of the 0, and when it is 0, then the ground state, sorry, the spectroscopic term would be the sigma, and then you will go for the spin multiplicity, that is 2s plus 1. Because both electrons you can see here in that case, however they are present in the different orbitals, but their spins are inverted. Okay, their spins are inverted. So you can write 2 multiplied by plus half minus half plus 1 equals to 1. And if you go for the parity, So again you see this is pi anti-bonding. Pi anti-bonding is always G-rate. So this is G-rate, this is also G-rate, and earlier this was also the G-rate because this was the pi anti-bonding. So if you put here the value, that is G multiplied by G, that will give you the G. Okay, and since you know this term is the sigma term, now it is essential to put the positive or the negative sign, right, for to know the sign of the wave function with respect to the sigma plane, that is sigma v. Okay, and since the trick is that whenever you have this value 2s plus 1 equal to 1, right, so you will put the plus value, and remember one, right, you will put the plus value for this one, right, and it is again you see this is actually what sigma g, and whenever you have the sigma g you will always put the plus sign over there, which I have told you in my previous lectures. So the term symbol would become sigma g1 of plus. Okay, so this is how you can determine the things actually. Okay, I hope this much of exercise is quite sufficient to understand the energy of the ground state and the excited state term. Okay, so if you want to determine the ground state and the your excited state, the energy order for them, so I can go for this, that also. So for this I have to remove this. Okay, I have removed for this one. And now for this oxygen you are having three symbols, right? First you are having 3 sigma g negative, and then you are having, say, next is you are having delta g1, and then you are having 1 sigma g plus. Now you have to decide actually which will have the lower energy, which will have the higher energy. So remember, there are certain rules. The first rule says that if you are checking the rule number 1, if the value, you will check the value of the 2s plus 1, right? If this value is the highest, right, then your ground state term would belong to your ground state would be like that. It is when actually 2s plus 1 is having the higher value. So if you are comparing all these three, right, 1, 2 and 3, so in that case the 2s plus 1 value is this one, right, so this will have the lowest energy in that case. That means this is the ground state. Okay, so you will straight away put this sign here. Now you see in the second step you are having the 2s plus 1, the value of the 2s plus 1 is 1. Again here the value of the 2s plus 1 is 1. So you cannot decide the energy of these two terms based on the spin multiplicity. When this happens actually, then you have to actually go for the value of the lambda, right? You have to decide the value of the lambda. Okay, so I am telling you, higher the value of the lambda, higher value of this lambda is having lower energy. It is having the lower energy, right? So if you want to check for this delta, actually the value is 2, and for this sigma the value is actually 0. Okay, so this value is higher, so this will have the lower energy, so you can put that sign. So this is the order actually. So this is the little trick to not trick actually, this is the method actually. However, you can understand these things rather quickly if you go for the group theoretical treatment, right? But in the simple case you can determine in that manner. First go for the spin multiplicity. Higher the spin multiplicity, lower would be the energy, and it would be the ground state. And when the spin multiplicity is same, then you can check for the value of the net orbital angular momentum. Higher the value of the net angular momentum, lower would be the energy. So if you follow this, then you will find this one. Okay, so this is how you can determine the things actually, right? This is quite clear. And see, please wait, I made a mistake here. This should be 1 sigma. Okay, this is 1 sigma g positive. Okay, fine. No, no mistake actually, right? So this is fine. Okay, so this is how you can determine. I hope this is clear to you. There is no problem in that. Okay, now this is the order of the energy, right? There is no problem in that. Now if you want to know the bond strength, order of the bond strength, so I can write it here. Order of bond strength, order of bond strength. So how you can go for the order of the bond strength? You know, whenever your electrons are present in the lower energy orbital, that means the bond strength would be very very high in that case. Okay, so if you see, if you compare the energy actually, right? So energy is actually lowest in this 3 sigma g, right? Energy is lower. That mean its bond strength would be the highest one. So if you go for the bond strength, then you will write in that manner, your 3 sigma g negative would have the highest bond strength. Okay, now if you want to compare the others, actually the you can go for the similar energy order. Now second is this one, so you can write delta g 1, and this will have the lowest energy actually, right? So whatever the lowest bond strength, so whatever the energy order would be there for the ground state and the excited state, you reverse that order to get the bond strength. Okay, now you can go for the bond length also, order of the bond length. So I can write here bond length order. So how you can determine the bond length order? It simply means actually, see, this order may confuse you, bond length. Okay, so what would be the order of the bond length actually, right? So whenever your bond is stronger, then it would be shorter, right? And whenever your bond is weak, then it would be longer. So this is something very very important, which you should know actually. Okay, so generally excited state actually will have the weak bond. So excited state, whenever excited states are having the weak bond, definitely their bond length would be the higher. So ground state term would have the lowest bond length in that case, and ground state term, here is here this one. That is, if you go for uh, bond length order, so highest bond length would be for this excited state. Okay, followed by this, and lowest bond length would be for the ground state, that would be 3 sigma g negative. Okay, so now the important question is that, okay, this is fine that ground state term is the 3 sigma g, that means the bond is the strongest, that means the bond length would be the smallest one. Now how we can compare the two excited states, the bond length for the two excited states, right? So in that case, you see both electrons are paired in the same orbital. They are present in the same orbital. But in that case, where electrons are present in the different orbitals, right? And they are having this spin. Okay, so whenever this happens, then you will go for the second option. Please remember this point actually, right? So excited state, for the excited state term, you will look for the value of the delta. Higher the lambda, higher the value of the lambda. So in that case, your delta, if you go for the lambda for this one, it would be 2 actually. For this is 0 actually, right? So this higher value actually will belongs to the higher bond length. Please remember this one, right? So this is how you can understand. Okay, so let us check actually. Here I have also written here, higher value of the lambda is having the lower energy. Okay, please let me correct it. That means it is having the lower energy, right? When it is having the lower energy, it simply means, okay, we cannot go in that manner actually. We cannot go in that manner. We simply actually solve this problem by using that energy relation. Okay, you actually, what you do actually, you invert the energy relation, okay, to get the bond length order, right? This is something very very important. Okay, and the next thing actually which is important, that mean stretching frequency. Okay, now you can go for the another, that is the stretching frequency. I can use the different color for this one. Okay, bond stretching frequency, bond stretching frequency. Okay, so for bond stretching frequency, whenever your bond is strong, then you will require higher energy to stretch that particular bond. Okay, that means the stretching frequency actually is directly proportional to the energy. Okay, and for this actually, if you go for this reason, then this would be same for this bond order, right? So I'm writing here, bond order is directly proportional to stretching frequency. Stretching frequency. Okay, so this order and that order. would remain the same. Okay, so this is how you can determine. So I hope this thing is quite clear to you. Now moving to the next one. Okay, next thing is the selection rules for the electronic transitions. Selection rules for electronic transitions. Selection rules for transitions. So this actually I have already told you in my coordination chemistry lecture, where I have determined the atomic term symbols. But let us recollect what we have learned so far. Say, first is actually the Laporte selection rule. Laporte selection rule. And what the Laporte selection rule says, that delta lambda, if it is equal to 0 or if it is equal to plus minus 1, then your transitions are allowed. Please remember. Okay, and then you may have your second point, spin selection rule. Spin selection rule. Then what spin selection rule says, that delta S, change in the spin multiplicity, would be equal to 0. When this happens, then it is allowed transitions. Okay, then you go for the number third, parity rule, or parity selection rule, or parity rule. Okay, so what it says, that this I have already told you, transition from G-rate to un-G-rate and transition from un-G-rate to G-rate are allowed. Okay, while G-rate to G-rate forbidden, G-rate to G-rate, un-G-rate to un-G-rate forbidden. Okay, so un-G-rate to un-G-rate is also forbidden. Third rule. And last, that is number 4, I can write here number 4. What number 4 says, that if a transition is having from this sign of the wave function, if you have the wave function positive, obviously it would be there on the sigma term. Okay, and when this is happening from plus to plus, it is allowed, and it is happening from minus to minus sign. Okay, so there is, we need to put the this sign, right? So these are the allowed transitions, while uh, plus to minus is forbidden and minus to plus is also forbidden. So please keep in mind these rules. Okay, so if you have know this much of thing, then it is easy to determine or to know the kind of the your transitions, allowed or the forbidden transitions. Now let us look what I have. So this question I am having, and this question actually I have taken from CSIR net examination 2011. So it is CSIR net, okay, December 2011. Okay, so you have to determine the transition. So please remember first point, how to actually start the question. First of all, you focus on that thing which is actually clearly visible or clearly recognizing. So the important thing which I have already told you, the first thing which I have told you, check actually for this transition, G to U or U to G. This is easy, right? So we are checking this one. So this is G to G. G to G is actually the forbidden transition. So this cannot be your answer. You can strike out this one. A is not correct. Okay. And the second one is, again you see, rest all, in the rest all cases you see here, this is U to G, that means parity allowed. This is U to G, parity allowed. This is G to U, parity allowed. So I am writing here, okay, I am writing for B. So for B actually, B is parity allowed. Parity allowed. Okay. Similarly, your C is also parity allowed, and your D is also parity allowed. So you have checked the parity. Now you can check the value of the Laporte selection rule. Laporte selection rule, what it says that you have to check for the delta lambda, right? So for the second transition, the value you see, actually I am going for the B actually, 0 minus 0, that will give you the 0. Okay, so if you go for the 0 minus 0, that means 0, and delta lambda equal to 0 is allowed. So how it is 0 actually? See, for this sigma term, the value of this lambda is 0, and here again in the excited state where the transition is happening, actually it is also 0. If you subtract, then you will get the 0. So B, C and D, they are actually Laporte allowed. They are also Laporte allowed. See, in that case, in the second case, right? If you go for the C, so I'm writing C here. So for C actually, transition is happening from your sigma zeros to delta 1. Okay, this is delta 1. So let us check actually whether it is delta 1 or not. See, this is 0, that means lambda equals to 0, then lambda equals to 1, then lambda equals to 2. So this is actually for sigma, and this is for your pi, and this is for your delta 2. But what the selection rule says that, this should be either this one, delta lambda equal to 0, or plus minus 1, but it is actually giving you the plus minus 2 here in that case. Okay, for C actually it is giving you the 0 minus 2, it is 2. That means C is not allowed, so you can strike out your C here. So your C is also, you can actually remove this C from here also, right? Now go for your pi and sigma. For if I am calculating for the D, so for D is actually what, this transition is happening from pi to sigma, so that is 0 minus 1, that is minus 1. So minus 1 is allowed, that means D is allowed. Okay, so D is allowed in that case. D, so far D is allowed, so far B is allowed. Now check actually the signs. Actually you see here, plus to plus allowed, and in that case you see there is no question of plus and minus here, so it could be allowed. So correct answer is actually, which is having the option B and your option D. So your option B is looking the correct, which is having two options, so you can mark this option B as the correct answer. So this is how actually you can you actually know how we actually determine the allowed and the forbidden transitions. Now moving to the next problem. Okay, this problem, the set of the allowed electronic transitions among the following. So this question actually I have taken from CSIR Net June 2012. CSIR Net June 2012. So how actually we can determine the transitions allowed or not. So let us check how we can do that. So here in that case, in the first one, here spin multiplicity is 4, here spin multiplicity is 2 for this one. So this cannot be allowed. Okay, since your G-rad and un-G-rad is not there, then second easiest thing actually to know the spin multiplicity. Then moving to the next one, here it is 3, so it is spin allowed. It is 1, it is 1, it is also spin allowed. It is 2, it is 2, it is also spin allowed, but it is 3 to 3, so all are spin allowed. Okay, so B, C, D, E all are spin allowed. Now let us check another thing, whether they are allowed or not. So next thing is left with the sigma and pi. So if you go for the B, if you go for delta lambda, that will give you sorry, this will give you 1 minus 0. How 1 minus 0? Lambda value for pi is 1, lambda value for sigma is 0, and that will give you the 1. Okay, and this is allowed. Okay, delta lambda equals to plus minus 1 is allowed, so it is looking like that your B is allowed, so you can mark this correct. Okay, now going for the C, again calculate the delta lambda. So what it says that, see in that case, for this delta your lambda is 2, and for this delta also lambda is 2, so you can quickly write 2 minus 2, that will give you the 0. It is also allowed. Okay, so transition C is also allowed. Now go for the last one, that is the D. In the case of the D, transition is happening from pi to pi, that means 1 to 1 actually, right? So delta lambda, if you calculate, this will give you 1 minus 1, that will give you the 0. So this is BCD, this is D is also allowed. Okay, so you can write D is also allowed. Now go for the E actually, right? So I am going for the E. What E says, delta lambda, so 2 minus 0, that is 2. Okay, how? See, for this delta the value is 2, and for this sigma the value is 0. So this is 2, and you know delta lambda only 0 and plus minus 1 are allowed. So this is actually forbidden. So you can strike out this, you can strike out this. So correct answer actually B, C, D. So option C is looking correct. Option C. So B, C, D, option C is correct one. Okay, now moving to the next problem. Okay, the problem says that for an electronic configuration of the two non-equivalent pi electronic transitions, which of the following term is not possible? Okay, now this question is looking very nice, very important one, and this question actually I have taken from December 2013, CSIR net, December 2013. So how to solve such kind of the problem? Say I am doing for your, say, term symbol which are allowed, which is possible and which is not possible. So let us calculate very quickly. Let us calculate very quickly how we can go that actually. So first, in the first case, this is 1, this is 1, and both are having electrons in it, and you know for this value is plus 1, for this value is the minus 1. If you calculate that quantum number, that means plus 1 minus 1 equals to 0, and when it is 0, it is sigma. Okay, then you can go for the spin multiplicity, that is 2s plus 1. Both are actually the paired spin, just 2 plus half plus half plus 1, that will give you the 3. Okay, so your term symbol would be 3 sigma. 3 sigma is there, yes it is. See, this 3 sigma is there, so B is possible, right? It is possible. Now you can go for another configuration, like let us actually draw the another configuration. So this I can give you the positive spin, this I can give you the negative spin. These are the possible transitions which I can put. This is plus 1, this is minus 1. If you calculate for the delta, that will give you the plus 1, and the minus 1, that will give you the 0, and that 0 would be your sigma. Now you can go for the 2s plus 1. So this will be 2 plus, sorry, not plus, it should be minus, no, multiplied, not minus, very sorry. So this is plus half, this is minus half, plus 1, that will give you the 1. Okay, so why actually I have taken this? Because this is having the plus half spin, this is having the minus half spin. So what is the term symbol which is possible for this one? Sigma 1. So this is also possible, 1 sigma is also possible. Okay, so this is also possible. Now going for the next one, what I can do actually, next thing which I can do, for this actually I have to remove this thing from here. So I am removing this one. Okay, now I'm going for the next configuration which is possible. See, this is pi, and these are the another pi pair. So what you do, put one electron here and put another electron here, and you know for this value is plus 1, for this value is minus 1, and again for this it is plus 1, it is for minus 1. Okay, if you calculate the delta, then it would be plus 1 and plus 1, that will give you the 2. Why plus 1 plus 1? Because electrons are there in the plus 1, so that's why I have put it this. Okay, and when this value is the 2, it simply means you will have the value of the this one delta, right? Then you can go for the 2s plus 1, and in that case both have the paired spin. You see here, this is plus half, this is also plus half. Okay, and when this happens, both are the plus halves, then what you can do, can simply write 2 multiplied by half plus 1, that is equals to 3. So term symbol would be delta 3. So delta 3 is also possible. So this is also possible. So you left with this one. Obviously D is not possible, so the correct option is the D. So how you can go for the D actually? Why this D is not possible in that case? Okay, D, why D is not possible? You know, you are having such things actually. Lambda equals to 1, 2, 3 and 4. Okay, and for this you are having the sigma, then pi, then delta and phi. Okay, and if you actually put the electrons right in those pi orbitals, you can never have that value of the 4. Okay, so this is the way that mean this D is actually is not the correct answer. Okay, now moving to the next problem. The first excited state of the hydrogen molecule is, so this actually example I have taken from a CSIR net June 2016. Okay, so for this what see the first excited state of the hydrogen molecule is, so you should know actually the excited state of the hydrogen. So it's quite easy actually guys. You see here, this is the molecular orbital diagram which you can draw for the hydrogen molecule. Okay, so this is what your sigma 1s, you know it is G rate, and second one is your sigma anti-bonding 1s which is ungirate. Okay, and see in the ground state actually you have both the electrons here, but in the question itself it is given that the first excited state. So for the excited state actually you have to remove one electron from here. So the moment you remove one electron from here and excite one electron with the parallel spin from here to here, so this is the configuration which you actually becomes sex like that. Okay, so and you know there is no net orbital angular momentum for the sigma orbital. So for this the value is the 0, value is the 0. So if you calculate this, that means 0 plus 0, that will give you the 0, and that will give you the value of the sigma. Okay, there is no problem in that. So if you want to calculate the spin multiplicity, that is 2s plus 1, that will give you the 2 multiplied by half plus half plus 1, that will give you the 3. Okay, so far you are having sigma 3. So now go for the G rate or the un-G rate. So it is un-G rate actually, right? So your electron is present in the G rate, and your electron is present in the un-G rate. So how you can write actually the parity? First electron is in the G rate, second is the un-G rate, and multiplication of G rate and G rate will become actually the un-G rate. So you will quickly write U here actually. Now you need to put the positive and the negative sign. Since your electrons are there in the sigma orbital, you always put the positive. Okay, so see guys, please remember that point. You may have the confusion that this value is having the 3, so you will put the minus here. It is not like that. Whenever your electron is, this sigma term is coming from your sigma orbital, see these are the sigma, this is sigma, and you are getting the sigma from here, then you will always put the positive here. Okay, so this 3 sigma positive U is the correct one, and this option is actually is the option D. So this is how you can actually solve the problem. Now moving to the next problem, what it says, the term symbol for the ground state of the boron. So boron, you know, boron molecule, see boron is, if I write here, boron actually is having the 5 electrons. Okay, so 5 plus 5, that means you are having the 10 electron. That means you have to write the electronic configuration of the 10 electrons. So how you write the electronic configuration? Sigma 1 is G rate, it is having the 2 electrons. Then sigma 1s ungirate, it is also having the 2 electron. Then you are having sigma 2s, it is also G rate, so you will write the 2 electrons. And then your sigma anti-bonding you have to put over there. So this is positive, this is 2s, this is ungirate, it is also having the 2 electrons. And finally you are having pi 2px, it is ungirate, that would be equal to pi 2py, this is also ungirate, and you will put one electron here, one electron here. If you count the electron, 2 to 4 to 6 to 8 9 10. So this is the configuration, and you know for this value is the plus 1, and for this the value is minus 1. If you calculate the lambda, that will give you the plus 1 and the minus 1, that is 0. And when it is 0, you can simply write the sigma for this one. Okay, and if you calculate the 2s plus 1, that is 2 multiplied by plus half, because both electrons are having the paired spin here, sorry, parallel spin here. Okay, that means +1, that will give you the 3. Okay, and you know your electron is present in the ungerade and your electron is present in the ungerade, right? So this is also ungerade if I write it. Okay, so if you go for the parity, then ungerade multiplied by the ungerade, that will give you the gerade. So far you are getting sigma 3 g, and whenever your g is there, g subscript is there along with the sigma, you will put the positive over there. Okay, so the moment you will actually put the positive, and then you will find, okay, it is fine, this is looking the correct one, but this actually will give you the wrong result. Why it will give you the wrong result? See, this sigma is actually, right, this sigma is coming from this pi actually, right? So you have to think about this one, 2s plus 1. When 2s plus 1 equals to 3, then you have to put the negative. If it was actually 2s plus 1, then you will write the plus. So 2s plus 1, 3 is there, so you will write the minus over there. So this is the minus. This is the correct answer for this one. And if you put that, then what would be your answer? Your answer is actually this one. Okay, 3 sigma negative g. This is how you can write it. Okay, so there is no problem in that. Now moving to the C, there is no see, these are the problems actually which has been asked in the CSIR net examination. And lastly, what we can do, we can check the last problem. Okay, and last problem actually you can write the problem of GATE 2012. Choose the allowed transitions. Okay, so how you will allow the, or not transitions actually, transition. In the question itself it is given the transition. Okay, so if you know, so what you have given in the A, your sigma g plus 1, and electronic transition is happening from here to here, that is 0, and this is uh, plus actually, right? So here you see the spin multiplicity is 1, spin multiplicity is 3, so it is spin forbidden. So this cannot be your answer. Okay, then go for the B. What is given here? Sigma g positive and 1, and next is sigma u negative and 3. So this actually you see here, this is 1, this is 3, this is spin forbidden actually, right? You can clearly visible here, you can clearly see here. So this is again cross, you can cross. Okay, then the option C, it is given here, your sigma g with plus sign and 1 here, and the transition is happening from sigma u plus 1. Okay, so you see here guys, it is parity allowed, so we can write allowed here, and it is also spin allowed, so this is allowed, there is no problem in that. And if you calculate the lambda, that means 0 minus 0 equals to 0, and for sigma 0 0, this is also allowed, and positive to positive is also allowed. So this is looking the correct answer. And the last option which was there in the question was just like that, sigma g with positive and 1, and it is just like that, u 1 and negative. Okay, so there is no problem, it is spin allowed, there is no problem, it is parity allowed, it is no problem, it is quantum number lambda allowed, there is no problem in that, but positive to negative is not allowed. Okay, so wave function sign is not allowed, so this cannot be your answer. So correct answer is the option C. So these are the problems which has been asked in the previous year CSIR net as well as in the GATE examinations. Okay, so I made the 2 lectures earlier, and this is the last lecture. I hope this will help you. Okay, so that's it for today guys. Thank you very much.